Okay, this is chapter 2. This is chapter 2, section 2.4 through 2.5, lecture number 4. And in this lecture, we're going to talk about 3 dimensions. So up to this point, we've dealt with 2-dimensional vectors and equilibrium in 2 dimensions. And so now we're going to go to 3D. Again, this should be stuff that you've seen before, but if you don't remember it or if it's a little fuzzy, that's fine. We're going to go through it. But it's important, I can't emphasize this enough, that the material that we're learning in chapter 2 is going to be used over and over again throughout the rest of the quarter. So get a good handle on it now. Oops, sorry. So first, I want to do this. I want to look at a XYZ plane, and let's talk about 3 dimensions. So let's imagine that we have a force. Now, the force I'm going to draw is going to, kind of hard to do it here, but imagine a force that's coming up out like that. So when I draw it like this, on paper, it looks like it's in just the XZ, XY plane, but it's really not. It's actually coming out kind of like that. Now, if you imagine you're above looking down on this, so you're looking down on the XZ plane. So let's imagine that this over here is the XZ plane. Let's even orient it the same way. So we have it like that. Let's say that's the X and that's the Z. If I were looking at this from above, then I would see something coming out like that. And that's exactly what I have. So I'm going to draw that. And that's my projection. So this is my force, and this projection we're going to call F sub H, for F horizontal. Now, to define this force, we have this angle here, which we're going to call theta, and this angle here, which we're going to call B. Now, when we first look at this, because F is in plane with the Y, then we know that in order to find the X component, or I'm sorry, the Y component of the force, then it's just simply cosine of that angle times the force. So backing up a little, normally we would have F, we would be given an angle like this. That would be theta Z, an angle like that, which would be theta X, and then this angle here, which is theta Y. Now, from this drawing, we can calculate theta X and theta Z, but we kind of do it indirectly. How do we do that? Well, first, let's see what we have with just F and FH. Now, with F, we know that the force in the Y direction is just equal to F cosine of theta. So the theta that's up here. So I guess we could label it sub Y for convenience. And then if we want to know what FH is, well, FH can be drawn as a plane. And normally it looks something like this and then like that. And I'll show you a better drawing of that in a second. But for now, just imagine that this is one plane. And so this opposite side up here, which would be the sine, F times the sine in this right triangle, this here is the same as this down here. So thus, FH is just equal to F sine theta Y. Now, once we have FH defined, because FH is in the XZ plane, then, and this angle here is phi, then we know that if we draw this line here, and that's my 90 degrees, that what's this side? This is sine, and this side is cosine. So what we can do then is we can say Fx is equal to FH cosine phi, and Fy is equal to FH sine of phi. So, sorry, not Fy, Fz, I apologize. And so as a result, now we have Fy, Fx, Fz. We can expand this because we know Fh substituted in here. We know that Fx is now equal to F sine theta y cosine phi, and Fz is equal to F sine theta y, and that's going to be sine of phi. So now we have Fy, Fx, and Fc all in terms of these two angles we know and the force we know. So of course, from the Pythagorean theorem, if we were to say F magnitude, that would of course be Fx squared plus Fy squared plus Fz squared, all square root. So we don't, and that would bring us full circle back to F. But also, what's important is that if we want to know those angles, so remember I mentioned theta x, theta y, theta z. If we want to know those respective angles, then we know that cosine theta x equals the ratio of the x force over the overall force, and cosine theta y equals Fy over F, and cosine theta z equals Fz over F. All right. So now let's go back to our slide, and we can see this drawn out. Now notice that here's our force, here's our theta y, and this is the plane that I talked about, how it's cut into. And you can see that this AB is the same in length as OC. So when we go over here, OC then becomes our FH. That's our horizontal force projection. Fy, by definition, then you can see is just F cosine theta y. And since this is the opposite side, then F sine of theta y gives us FH, just like I showed you. And so we know that both the angles theta y and phi now define our force direction. So another thing is that, and this is repeating a little bit, but here we have our theta x, theta y, and theta z. And this shows you how when you actually have a three-dimensional drawing, you can see that theta x can't be just simply garnered from looking at F. It's actually a sweeping angle towards that axis that can't really directly be calculated unless you have the appropriate components, being Fx over F. So the other thing to think about is that once you have these angles, you also have what are called the unit vector. And so the unit vector, which has a magnitude of 1, is essentially the cosine theta y, cosine theta z, and cosine theta x. The cosine of those angles give you the respective magnitudes of those I, j, k components. Now, backing up, you want to visualize the unit vector, and this is how you visualize it. You define the vector in space, and then you write it in terms of I, j, k. Now, let's see if no, I didn't. So going back to the paper with the unit vector is lambda is equal to lambda x plus lambda y plus lambda z, being I hat, j hat, and k hat. And so you may have seen this before. So lambda xi, lambda yj, lambda zk, all hat. So another way we could write this though is we know that lambda is equal to cosine theta x I plus cosine theta y j hat plus cosine theta z and k hat. And as such, lambda squared, or if we square this, we get 1 is equal to lambda x squared plus lambda y squared plus lambda z squared. Or 1 is also equal to cosine theta squared plus cosine theta y squared plus cosine squared theta z. So I guess the correct pronunciation is cosine squared theta x, cosine squared theta y, cosine squared theta z. And so that also gives you 1. And so all of these are just tools that you can use. If you don't know one value, you can find the other. And so sometimes you'll have the magnitude f, and you want to convert that to the vector f. And so using what I've shown you, you can do that. Now, that's not all that exciting at this point. All we have is a vector ijk, but now in chapter 3 and beyond, we're going to learn what we do with that vector. How do we actually calculate something of use? So let's look at an example. There we go. And so this is an example that I want you to try on your own, and then I'll walk you through it. So typically in class, I would let you sit for a few minutes, talk to your neighbor, work on it. But in this virtual society, you're going to pause the video and try to work on it. Now, ignore the 450. That's just a different problem. It has nothing to do with the 600. But we have a 600 Newton force here. It tells us that 25 degrees, or theta, is equal to that, and phi is equal to that. So what I want you to calculate is fx, fy, fz, and cosine theta x, theta y, and theta z. So go ahead and do that. And then when you think you've gotten it through, then come back and check the answer. So now I'm going to assume that you have given it your best shot and either got it right or you didn't. But the struggling is the best part. And so the more you work at it and try to figure it out without resorting to looking at my solutions, the better you're going to be. So let's go ahead and draw this real quick. Let me pause the video for a sec while I do that. Okay, so this should look just like what you just did. Now here I've drawn the problem. Now normally I'll work them through live. This one I think I'm just going to show because I think it's reasonable enough. It's just plugging in the equations that you can follow. So you're given your find, which is something you always want in your problems. So I'm given force in space. There's my angles. This is what I want to find. My governing equations. So this is straight out of what we just talked about. F is F cosine theta. We know Fx is F sine theta cosine phi, F sine phi. FC is F sine theta sine phi, and that's just directly from the derivation we just got done. We know theta y is given, and then we know that these are going to be equal to Fx over F and Fz over F. So really, we know this is 600, and we know those angles, so it's just a matter of plugging in and calculating. So if we go ahead and do that, we have 600 cosine 25 gives us 544. If we want FH, it's F sine theta. So FH 600 times the sine of 25 gives us 253.57. Carry that down to FX, 253.57 cosine 30, using that equation right up here. And we get FX is 220. Do the same for FC. We get 126.8. And then we plug those respectively in to find theta x and theta z. And there's our angles. All right. So we have theta x 68.5, theta z 77.8, and theta y was given. All right. So that's how you do that. That's how you convert. And so that will come back in some problems to do, but that at this point should be second nature to you. You just need to practice. So going back, we have, here's our example. So kind of got ahead of myself. Now here's another example. This is adding forces in space. And so now this is where we're going to start. This is where we're going to actually take a known system and we're going to use the fact that we know a scalar value, in this case dB, and we're going to convert that scalar 385 newtons to what the vector dB would look like. And so typically when you see a problem like this, you first, again, like before, you want to write down your given. So what are you given in this problem? What are you trying to find? And then finally, going ahead and drawing the vector dB and then working the problem. Now, we know we're D, we know the point of application. So because the point of application is, and this comes from the reading the problem. So let me back up a little bit. So when it says a frame ABC is supported in part by the cable DBE and through a frictionless ring at B. So we know that DB is just one cable, and as such, the cable should have the same tension everywhere. Then if we know that that tension is a magnitude of 385, determine the components of the force exerted by the cable on the support at D. So this is important when you read these problems. When it says on the support at D, that indicates that the vector is going to be going away from D. So it's anchored at D, but the vector is going to point from D to B. Now you might ask, well, what about E? Doesn't that matter? No, it doesn't, because all we're asking right now is what is the force in the direction of dB. We're not asking what it does to the system or anything like that. We just want to know what that is. So to do this problem, you know the equation for tension is going to be tension equals the scalar value times the unit vector. And so the unit vector will just be what you find within the direction dB. So go ahead, take a few minutes to draw this out, sketch it, solve it, and then come back and work and look at the solution. Okay. So you've worked out the solution, I hope. Well, let's go ahead and walk you through it. So here we have our sketch. So I've drawn our sketch with our dimensions. Sometimes it's easier, depending on the complexity of the sketch, to just say dimensions or millimeters, forces or newtons, and that way you don't have to worry about putting that on there. So we're trying to find the direction dB, that tension vector. We know it's going from D to B. All right. So remember that our governing equation, tension dB equals the scalar of dB times lambda dB. All right. Now, this, as I said, there's some things that I didn't really present this equation up to now. That's talked about in your book, and so I recommend is skim the reading in tandem with looking at this. But remember the unit vector. Another way to write the unit vector, lambda dB, is, and this again is nomenclature by your book, but lambda dB is equal to the line dB over dB. So this is the vector and that's the magnitude. All right. So how we're going to get that, let's just find that first. So we know that lambda dB is equal to, now we want to go, so now we want to look at our directions. So how far in the X, if we're going from D to B, we're going from, D is at the YZ plane, so that's the origin. So we're going to go out 480 millimeters. So that's going to be 480 I. And then we want to go in the y direction. Well, D is up here, B is at the origin, so we're going to go down a negative 510 in the y. And then the Z, D is at 280, it's going to go out to 600. So the difference, if you normally you'd say B minus D to get that, but 600 minus 280 would give you 320. So we have to go out 320 in the positive K direction. So what we're going to get is plus 320K. And then we're going to divide that by the magnitude, which is 480 squared plus negative 510 squared plus 320 squared, all square rooted. And if we do that, then we're going to get, and simplify, we get lambda dB, and this is a matter of preference. You can either leave it as a fraction, as 480 over whatever this number is. This number actually turns out to be 770. Sorry, let me erase that. 770. So you can just write 480 over 770i if you like that, or you can just write it as a decimal. If you do a decimal, I wouldn't keep more than 3 decimal places. So 6, and I transpose that. 623i minus 0. That's i hat minus 662j hat plus 0.416 k hat. And when you write decimals, please put a 0, because if you just leave it out, I can't tell if that's a fly speck or an actual decimal point. Whereas if you have a 0 there, there's no question. Okay, so now we have that. And so then finding the tension vector is just a matter of multiplying through. So tension dB is just going to equal that value, 385, right? So 385 newtons is the scalar of dB, and then multiplied by 0.623i minus 0.662j plus 0.416k. And so if we simplify that, we get tension dB equals 240i minus 255j plus 160.0k. And that's in newtons. And that's our answer. And that's all we got to do. All right. So let's go back to our lecture. And so we've done that problem. So let's do another. So we have 2 more now. And this is the worksheet. And so when you see example 4 worksheet, that means you want to make sure that you've downloaded the appropriate worksheet, which on Canvas on the given lecture day. It should be right below the link for the YouTube video for this. And so now we're going to look at this one. Now this one's a little more challenging. This is basically taking everything we know up to this point. So we have the spur gear here, and we're looking at the force acting right on the gear at the origin. So we really don't care about the gear per se. We just know that at that very point at the origin, you have this contact of these 2 vectors. You have a 180-pound vector coming out this way, and you have this 50-pound vector coming out that way. So you're essentially going back to what we did before, where we added 2 vectors. In 2D, it was easy. This is a little more challenging, but not. So one thing to notice right away is that with this force 2, you have the angles given to you. So if we do that, we know that cosine theta of the respective angles will give us the unit vector components, which then we can multiply by 180, which will give us our force 2 vector. And we can do the same thing with F1. And so one thing, sorry about that. I just wanted to here we go. I want to point out that theta x, theta y, theta z are given for F2, but then also for F1 that it lies in the YZ plane. So you have a 7, 24, 25 triangle in that. So go ahead, take this time now to solve this. So you're going to figure out what is the vector of F2, what is the vector of F1, add their components, and just leave it as a vector. So go ahead and work on that, and we'll pick up and start solving that here. Okay, so hopefully you've taken the time to look at this problem. So here I've drawn it out here. Now, so I have my F2 over here, which I've defined as 180, F1 as 50. I know that this is a 7, 24, 25 triangle. So let me go ahead and make sure I've written that in there. And so that we know looks something like that, where that's 7 and that's 24. So let's look at each one. Well, let's look at F1 first. So we know that F1 vector just equals scalar F1 times lambda 1. Lambda 1 is 0i plus 7/25 j minus 24/25 k. Therefore, F1 is equal to 50 times 0 plus 7/25 j minus 24/25 k. And you can kind of see with the 50 and that it's going to cancel. So you're going to end up with F1 equal to 0i plus 14j minus 48k. So that's our first one. So let's look at our second one. Now, I'll leave a space here. Actually, let's just jump ahead. So F2 is going to be equal to 180 times lambda 2. Sorry, I should have put a vector up there because that is. So we have F2 times 180 times lambda 2, and it's pounds. I'm not too much of a stickler about putting units within the problem. Some professors are, but as long as you have them at the end, that's the main thing. And then these earlier simple problems, there's not very many units, so you'll have to develop your own style as you go. Some may say it's heresy. But so here we have lambda 2, the unit vector of that. So remember that what we defined it as, we can say that lambda of 2 is just equal to cosine theta xi plus cosine theta y j plus cosine theta z k, right? So we know the angles, we plug them in. So write it out as F2. So F2 equals 180 times cosine 60i plus cosine 60j plus cosine 135k. And so we do that, we know that's half. Let's square root 3/2. So we should get F2 equal to 90i plus 90j minus 127.3k. And now we know that resultant equals F1 plus F2. So if we bring in our other one, F1, we know that that's going to be equals what? 0i plus 14j minus 48k. So our final answer is 90.0i plus 104.0j minus 175.3. Sorry about that. Okay. And there we have it. So that's our resultant vector. So that's just adding two vectors in 3 dimensions. All right. Okay, we're almost to the finish line. So I'd like to do one more example, and that'll wrap it up for this part. Now in lecture 5, we're going to actually apply this to a 3-dimensional problem. So we'll actually solve something. So let me go ahead, go back to that. And so let's go to the next one. All right. And so, well, actually, we are going to do the balloon problem in this one. So, all right. So if the resultant force acting on the hook is 200I, negative 200I plus 800J plus 150K, determine the magnitude and coordinate direction angles. So this one, we're going to work backwards. So we're given the resultant force, but we don't know what F is. So we know the resultant force direction. We know F1's direction because we have this drawing. Now this one's a little trickier due to the drawing. In this case, there's this 30-degree angle that's here, plus this line here is going at a 345. So it takes a little bit of looking to fully understand what's going on here, but study it. And because you will come across problems like this in other avenues where this is where you have to start and you don't want to get stuck on this. So once you figure out F1 as a vector and you have FR, then you can solve for F. Once you know F, then we know that we can easily find the angles from that, okay? So go ahead and take a stab at that and come back and I'll show you how to do it. Okay, so you've made your effort, you've solved it, and you're saying to yourself, this is so easy. When is he going to challenge us? When is he going to make this stuff harder? Well, trust me, it's coming. So, all right, so here's our problem. We have F1, we have our angle, we have that, and we have the alpha, beta, gamma. So I thought I'd take a little bit to show you the angles. Now I realize they're not trivial looking at, and the resolution of the drawing can be a factor. Try to make it as clear as possible. But so first off, let's look at the planes if you're having trouble seeing where F1 is going. If we look at the YZ plane, for example, if that's saying if I'm looking from this direction in at the YZ plane, then F1 looks like this. That's where the 345 comes from. Okay, I'd be looking that way. Now, if we're looking from above, from the XY plane, then that's where the 30 degrees comes from. So hopefully that gives a little better sense of how this thing is solved. I think that it will be of benefit to kind of take practice on this because over time you'll start to recognize how these things are drawn. All right, so now we have we know that our force F plus F1 equals the resultant. So essentially the resultant minus F1 is going to give us F. And that's what we're looking for. So let's first let's find the components of F1 since we already know what R is. Let's find F1. So F1, and I'd like to somehow leave this up here. Let's see if I can give you a little more space to see that. Try this. See it as I draw it. So F1 Z, so that's the Z component of F1, equals 3/5 of 600. So what that's gonna, that's the direct force. So this would be akin to before when we found the Fy force, we found it directly from the force times cosine theta. Well, that would be the same thing here. This 3/5 would be the same as the doing that. So that gives us a value, and it's negative. So that gives us a value of negative 360 pounds, which again, equal, that's heresy too. So don't do that. So I should have written it here. So F1Z is negative 360. All right. Pretend that didn't happen. Don't tell LoCascio. And so now let's look at F1. Now this is the horizontal. So this is the projection. Remember, we want to find that. Well, we know that the projection is going to be that 4/5, because if you're looking from below up, think about looking from underneath up, then that 4/5, what would be along the XY plane. So we know that's equal to 4/5 of 600, which equals 480 pounds. All right, so we have the H component, we have Z. So now we need to find the X and the Y. And so of course the X and the Y are going to be using the 30 degree. And you may have already figured it out that if we know FH, then we have this triangle back here. And so this has become my FH. And so drawing that like that, you can see that this will be Y, or cosine, and this will be my sine. And so now we have it. So I'll go ahead and draw F1Y equals FH of 1, F1H times cosine 30, and F1Z equals F1H times sine 30. So we have essentially 480 times square root of 3/2. That's what cosine 30 is. And this is equal to 480 times a half, right? Because that's what sine 30 is. So we get 416 and 240. All right. There. Okay, so let's draw out the whole thing. So now we know that F1 equals 240 I plus 416J plus 240K, and that would be, I'm sorry, 360. I'm sorry about that. That would be negative 360K. There you go. And we know that we want to subtract that from R. So I'm going to write R down here, and that's given as negative 200 I, 800 J, and 150 K. I'll just write it out like that. F1, 240, 416, and negative 360. We got to subtract. So what do we get? We get a negative 440i plus 384j and plus 510k. So this is F, big bad F. So now we have that, we can find our angles and we're done. So we know that alpha is equal to the inverse cosine of negative 440 divided by the magnitude. But what is the magnitude? Well, the magnitude, because you already would have done that, is 775. So that's F. Sometimes you'll see a line underneath it, but that's what that is. So if I square root, I get 775. So, and in future problems, I may skip that. I may just assume that you know that this is the relationship that you need. And so alpha equals, because that's negative, it's a angle greater than 90, so 124.6 degrees. Beta equals cosine minus 1 of 384 over 775. Beta is 60.3, and gamma is cosine inverse 510 over 775. Gamma equals 48.8 degrees. All right. So there you have it. You have the angle, you have the angles, you have the magnitude, and we're done. So not so bad. So I think the biggest challenge on this problem, again, was reading the original picture. But once you get through that, things aren't so bad. All right, so now there's one last problem I want to do, and this has to do with the equilibrium in chapter 2. And we're going to pick up equilibrium again, but this is a three-dimensional equilibrium. Now this problem somewhat, it's a little longer than the other ones, but once I go through it, the good thing about it is if you really understand this problem, it's going to come back in chapter 4 and we'll add a little bit more to it, but there's not a lot more that we will have to do. And I guess to say that more simply is it's a very good foundation type problem. So let me go ahead, share back with that. And so here we have our equilibrium in space, okay? So equilibrium in space, same as in planar. And as before with equilibrium, you want to sum the forces in the x, sum the forces in the y, sum the forces in the z. The difference here is that in the past we had two equations, two unknowns, pretty easy to do. In 3D, we sometimes end up with three equations, three unknowns. Still doable. In fact, your programmable calculator should be able to do that without much effort. If you're using a TA89 or TA84, there's a lot of online information about how to program it to do that. You probably already done. So, and that's fine. Typically, I like you to show your work, but if you set up the three equations and then just say done by calculator and then give me the answer, that's fine because it's not an algebra class, especially on a test or quiz. So here we have our problem. We have our hot air balloon and full of lots of hot air. And we have our, we want to first draw the free body diagram for it. And we want to find, what we're trying to do in this one is we're trying to find the tension in the three cables. And we're also trying to find the buoyant force that the hot air is causing this. So the way you approach this is you're going to draw the free body diagram, you're going to sum the forces in the x, y, and z, and then you're going to separate them into their respective components. All right, so let's go to the next slide. And so here it is, more hot air. I'm equal opportunity when it comes to grilling people. So here's the actual problem. So 3 cables are used to tether the Bernie balloon as shown. So you want to determine the vertical force P exerted by the balloon at A, so A being here, knowing that the tension in cable AD is 481. So Here's cable AD, you know that scalar value. So you ask, well, how do I do this? Well, first thing I would do is draw your free body diagram. So you know you have a force coming up, and then you have 3 forces going down at these respective vectors. So go ahead, find those values. Find the vector AB, find the vector AC, find the vector AD. Once you do that, you're going to multiply through with your scalar value. Now the scalar value of AB and AC is unknown at this point. So you're just going to multiply it through by tension AB, tension AC. But you do know AD. Once you have that, you know that all of the X components have to equal 0, all the Y components have to equal 0, and all the Z components have to equal 0. So you can actually solve directly. In this problem, because AB and AD lie right on the line, you won't have to do 3 equations, 3 unknowns. You can solve it fairly directly. So this one's a little more challenging. I normally like to walk you through it in class and have you work a little bit, but that kind of precludes, or it's precluded here given what we're doing. So go ahead, take a stab at it. I'm going to pause the video, or you pause the video, and then come back and look at the solution. Okay, so, all right, so hopefully you've had a chance to try it, and my hope is that you got through it. Not, don't despair. This is probably the hardest problem we've done so far. And so here I have my drawing. I put my dimensions down where my respective components are. So what do we need to do? Well, the first thing we need is a free body diagram. So let's go ahead and do that. So free body diagram is going to look something like this. You have P going up, right? You have TAB, TAC, TAD. So that's what your free body diagram looks like, all right? So hopefully you got that. So you have 3 forces down, 1 up. So we know that again, that whatever forces are in the Z have to balance, whatever force in X have to balance, whatever force in the Y have to balance. So let's go. So we know that our governing equation for this is P plus tension AC plus tension AD plus tension AB all equals 0. All right. So now we want to find the directors and the components. So that's our first part. So 1, I'm going to say find vectors and components. All right. So with that, I'm going to say tension AC, right, equals times lambda AC, all right? And then the same for the other ones. Tension AB equals all right, so there they are. Those are the 3. So AB, AB, AD, AD. All right, so there's the 3. All right, so then the next part, and for this, I think I'm reasonably comfortable just showing you what's written instead of redrawing it. So let me kind of cover it up and go through it. So here, this is the AC vector. So we know it's 2.4 meters in the I, negative 5.6 in the J, 4.2 in the K, and divided by the magnitude, just like before. So we multiply through by TAC, and there's our unit vector, and we get that, okay? So the main thing is to get these. Now this is, again, it's just review. So you're going to get TAC. You're going to do the same thing for lambda AB. In this case, you'll note that there's no K component, and you're going to get that one. You're going to do the same thing for lambda AD. And in that case, you get no I component, and then you get that. So if you're still not comfortable with this, I would take a moment to do this on your own, find these, make sure you calculate them correctly, and then check. But now you'll notice I have all three of my vectors. Now, AD, you'll notice I did deliberately leave it as an unknown, even though I know the value. So what is the next step? Well, I have these three equations, so I know that the I component, so this I component, that I component, have to be equal to 0. All right. I know that that J, and that J plus the P have to be 0, and I know these two K's have to be 0. So what I do is I combine them. So what I've done here is I've written out the equations. I've written them out just so they're better in line. And now I've summed the forces in the X, Y, and Z. So these are my equations, as I said, that I just did, putting a 0 as a placeholder. And then I went ahead and said, okay, for all the forces in the X, what are the respective components? So at this point, because I'm dealing with just the X, I can drop the I, you can drop the J, you can drop the K, and all I'm left with are these. So as you'll notice with the Y, I have these 3 plus P equals 0. With this, I just have AC and AD. Now, I do have 3 equations and 3 unknowns. That's true because I only know AD. I don't know AC, AB, or P. But notice the way these are set up. Notice that in this Z, I know AD and I don't know AC. So I can plug in 481 here and solve for AC. Once I know AC, I can plug that up here and solve for AB. And then I know all 3, I can solve for P. So this one's a little more straightforward than that. So I go ahead, just like I said, and I solve. I have TAC equals that times 41. I get TAC to be 430. I push that into the X, the sum of the forces in the X, and I solve for TAB. I get that, put it into the Y, put all 3, and you get P. And I get 926 newtons going up. Okay? So I would go through that. I know I went through that quickly with the solution, but I think it's something that it's more time consuming than more mainly because of the math, not because of the concept. And we're going to use this over and over again in the 4th chapter. So, all right. So that is it for chapter 2. That brings us up to speed with everything we need to know. So in our next chapter, or I'm sorry, lecture 5, we're going to start with chapter 3, and we're going to deal with moments. Thank you. And let me see. Oh, wait, I do have a conclusion screen. Sorry. There we go. So chapter 3, summary. So this is what you should come away with in chapter 2. Add 2 or more forces using trig or components. And you'll notice with the first homework assignment, the first few problems I meant you to use trig, not components, because that's what we focused on. If you didn't, that's not the end of the world, but do try to practice with both methods. And then also how to draw a forced triangle, find planar equilibrium, and then the last 3 bullets we just did. And most importantly, survive this confounded virus. All right. Thank you, everyone, and I will see you in lecture 5.